Hello, Dr. Ron England coming to you from Daytona State College, and today I'm going to talk to you about the data structure series binary trees. So let's first talk, before we start talking about binary trees, lists, stacks, queues, graphs, they're all made up of nodes. So the node of a binary tree really can have 5 different properties. It doesn't have to have 5 properties, it's going to have 5. The parent, left and right node, and then internal to the node it might have an ID, and it can also contain some content because it's useful if it actually has content. So if you look at each node of the tree as existing with these elements, or at least a fraction of these elements, it does need to have a left and a right, and it should have content because otherwise it has no purpose. You can easily kind of envision how they can be put together into trees. So the binary tree itself, and if it's a binary tree, it really is implying that each node has a left and a right. May or may not have a parent. The top node does not have a parent. All the other nodes would have a parent. But each individual node has a left and a right. Now there are types of trees that have more than 2 children per each individual node. And we're going to talk about some of those. But your standard binary tree has this. What it does is it gives you a capability of doing many types of things in computer science with this type of structure. Obviously the top of the tree is called the top, the very bottoms are leaves, and then branches are just subsets of trees that are in themselves trees. They can also be called subtrees. So if you're going to go through the concept of leftmost traversal, because you need to be able to traverse the tree, if you start at the top, what that means is that you would go from A here to B to D, staying on the left side. When it gets down to a node where it can't go any further, it's going to go back up to where it has a node it can go another direction. So it's going to go back to B, back to A. Well, now that you've traversed the left side of A, you're going to start traversing the right side of A, which gets you down to C. So C is now a subtree, and it's still leftmost traversal, so it's going to go to E, back to C, and then to F. So your traversal, if you actually looked at the node traversal, it would be A, B, D, B, A, C, E, C, F. Okay, and of course the back traversals, you may not actually access the node properties, but you have that you're going to be going up and down the tree. There's also rightmost traversal, and algorithms for traversal follow specific patterns. This one is a simple pattern called leftmost traversal. So let's look at some types of trees. So a common tree, the AVL tree, and the one I'm going to show you in code here is an AVL tree. The subtrees never actually differ by more than one layer, and the one I'm going to show you is an AVL tree, and I'll show you how it's algorithmically coded. Another type of tree, which is a very common type of tree, which is the heap, would be considered a complete tree. Now what we mean by a complete tree is that you just don't have subtrees going off in one direction. The tree finishes all the subtrees for a layer before it moves on to another set of subtrees. But the heap has an interesting characteristic in that the value of the parent node is always going to be greater than the value of the descendants. So that means if you add a node to a tree, you have to have an algorithm. Suppose I add 40 to this. Well, it's going to have to know where to put it, which means it may have to move some of the existing nodes up or down. So that's part of what you'd have to deal with when you're dealing with a heap. Okay. Some other ones like the trie, T-R-I-E, and radix trees. Those are ones that I thought were very interesting. There's many more tree types that we can look at here. They're used for things like spell checking, and the T-R-I-E, the trie, is very useful for spell check systems. And actually, the top node in a typical spell check would have 26 children, one for each letter of the alphabet. So 26 children. And then, but I'm not going to go into the depth of how these work. Needless to say, at least looking at a couple types of trees, the type of tree that you select for a specific type of purpose is very important. Some sort well, some are able to easily be modified. So designing a tree for a specific purpose or using an existing type of tree for a specific purpose is one of the things that you do as a computer programmer. Now let's actually look at some tree code. So here I'm going to look at some tree code, and in this case I'm going to first I have a button here that when I click on the button, it calls a function called create tree. And all I'm going to do here is I'm going to instantiate a new binary tree, and I'm going to add nodes A through H. And A through H are strings, and they're just the content. And then I actually output this. Well, since we create this new binary tree, let's go up and look at what actually makes up this binary tree. And it shouldn't be any secret. Okay, the binary tree, and this is in JavaScript, so it's a function, and it has one property, top. That's it. It has a function, a method, add node, and what it'll do in the add node is it'll look to see if the top exists, and if the top doesn't exist, it makes the node that you've added the top. It actually instantiates a new node and adds it and makes it the top. Otherwise, it goes to the top and tells the top to add the node. So obviously there's going to be a function of the node to allow you to add nodes to a node. Well, in a tree, if you add a node to a node, it's just going to go down and say, well, do you belong in one of my children? So let's look at the node. Okay, so the properties of the node here, parent, left, right, content. I don't actually use the parent in this example at all. In fact, you don't even have to have this property. But left and right, obviously, for a binary tree, left and right are the nodes that are below it. So let's look at the function add node. You just saw that if you added a node to a node, it knew what to do with the node. So in this case, I first look to see if there's a left node. And if there is no left node, I make that node the left node of the current node. So I actually make a new node, I instantiate a new node, and I make it the left node of the existing node. And then I return. If there's no right node, I do the same thing for the right. I make the node on the right, this dot right, equal to the new node. Well, if I have a left and a right, the next thing I'm going to do is I'm going to go, let's find out how many children, which would be children of that node, exist on both the left and the right. So I actually have a method called number of children for a node, where it counts how many children it has, and I compare the left and the right, and if the left is less than the right, I add the node. I go down and I add it to that left node, which is going to do the same exact logic that you just saw. And if the left is greater than or equal to the right, it's going to go to the right and add it to the right node. So basically it builds the tree. And if you look at the tree that I built, you can actually see that it's a balanced tree. A has a B and a C, and B has an E and a G. E and G are both blank. So A has B. C, okay, is also a subnode of A. So here's the left side of A, and here's the left side of a right side of A, which has its own left, right, and then a node off of them. So it follows a logic pattern that keeps the tree relatively equal, or like an AVL tree. It never goes more than one. So let's go one little step further. You can see that this makes sense. The last thing I'm going to do is I'm going to show you the prototype function number of children, which is a method of the node, and it is a recursive call. So what it does is it says, okay, let's first say that the value of n, the number of children you have, is 0, and if the left is not equal to null, then there's a node there. So you're going to add 1 to n, and then ask it how many children it has. That's it. Now, if it has a right, okay, then it's going to add 1 to whatever it was before, so n equals n plus 1, because now you got a right node, and it's going to ask the right node how many children it has. And it adds all those together and it returns n. So you can easily get recursively the number of children that you have. Now that's as far as I'm going to actually go into this. I think that you should be quite capable of following the code that's available here. Trees are more complex now than we're dealing with lists, but they're not so terribly complex that they're not understandable. And there's lots of great capabilities with the tree that you're going to get to work through with your homeworks. So hopefully everybody here will enjoy this lecture on the understanding of trees. Good programming. Hope you enjoyed it.